This is the Vale of Eden, a broad valley that extends between the Lake District and the Pennines. And the topography here is in part a relic of a topography of the past, 250 million years ago in the Permian. But this wouldn't have been a lush green area then, it would have been a parched desert. And this is an artist's impression of what the vale would have looked like then. Sand dunes occupied the middle of the valley, with the Pennines beyond the steep scarp that we can see today. That formed the eastern edge of the valley. And this first developed 250 million years ago. And in the foreground is a dry stream bed, a wadi, down which water would have occasionally flowed. So how do we know the Vale of Eden was a hot, dry place back in the Permian? Well, there is evidence in the rocks here. Between us and the Pennine Scarp in the far distance are Permian rocks. They lie stratigraphically above these gently dipping limestones. So if we observe their characteristics and compare them with what we can see in modern desert sediments today, we can work out their processes of deposition and their depositional environment. So let's visit another valley, Death Valley in California, and look at the sediments accumulating there.
Death Valley is part of a wider arid region of the southwestern USA, where deserts largely owe their existence to the rain shadow caused by the region's mountains. Any water carried by the prevailing winds from the west tends to fall there, and rarely on the sweltering valley floor. Even though Death Valley is not typical of the world's great deserts, in this limited area we can observe all the important desert processes, and so judge which of them will leave their mark in the sedimentary record. A variety of sediments are formed in deserts, and the starting point is the weathering and erosion of the mountains. Disintegration of the bedrock produces scree slopes mantling the mountains. These spectacularly shattered boulders were weathered by a process common in arid areas, salt shattering. Salts within the rocks dissolve in water from dew and the limited rainfall. Then, with the enormous rates of evaporation, crystals grow, and their expansion splits the rocks apart. There's only one agent to transport this coarse weathered debris: water. Though rain may be rare in a desert, when it does come, it's usually torrential. And with so little vegetation to hold it back, water runoff is rapid, funneling into canyons to produce flash floods. Look at the sediments left against the canyon walls.
During a flash flood, the rapidly moving current transports a good deal of material. Some of it has been deposited in this sharp corner of the canyon here. The strength of the current is apparent both from the amount of material and also the size of boulders, such as this one here. It's really quite a size. Now, although the canyon is bone dry at the moment, having seen deposits like this piled up right up here, it's very easy indeed to imagine the water current boiling and churning its way off down through the canyon.
Most of the debris is carried out through the canyon and dumped at the mountain's edge in a conical accumulation of poorly sorted sediment known as an alluvial fan. Some of these fans are gigantic, up to 10 kilometres long and over 300 metres high. They're formed because once the raging floodwaters are released from the confines of the canyon, they spread out, losing depth and velocity, so they can no longer transport the coarser sediment. Broad flood channels run down the fan. Over time, they migrate, depositing sediment over the entire fan. But this is a slow process, and the darker areas of the fan mark parts which have remained undisturbed for many years. These channels are broad and flat, and their floors are covered with a characteristic network of smaller channels formed by braided streams. The braided network consists of short channels and intervening bars. As the sediment-laden floodwater sweeps down the slope, so there's a repeated clogging of these channels. As one channel clogs, the stream migrates to cut new channels that repeatedly divide and meet around the low bars. And it's the migration of these braided stream networks that's responsible for the fan's detailed structure.
This channel wall shows the structure of the alluvial fan. The sediment is very poorly sorted indeed. There's sand and silt, there are cobbles, there are even some boulders. Overall, water deposition has produced a crude lenticular stratification. Some of the beds are quite fine, but others are much coarser. This variation in the sediment size is a reflection of variation in the strength of the water currents.
An alluvial fan may be constructed from a spectrum of events, both water lane deposits as well as poorly sorted muddy debris flows. Continued subsidence of Death Valley's floor has allowed hundreds of metres of alluvial fan sediments to accumulate. On at least the smaller fans, water will flow across the toe of the fan and out onto the flat valley floor, known as a playa, to form a temporary lake. Since water at the base of the fan flows gently, it can only transport the finer sediments, so the playa sediment is composed of fine silts and clays. As the playa dries out in the intense heat, desiccation cracks form. In other areas, the water flowing onto the valley floor contains high concentrations of dissolved salts. Evaporation causes these to precipitate, forming white blooms of halite, common salt. These are deposits precipitated in an ephemeral lake, a playa lake. On the borders of Saudi Arabia and Oman, at the edge of the empty quarter, there's an even bigger playa. The huge polygonal ridges are where the salt crust has been forced up by expansion as more salt precipitates in pore spaces as the lake finally dried up. Apart from the ridges, the playa is absolutely flat in every direction. For all its scarcity, water is of major importance in shaping the arid environment of deserts. That's clear from the creation of alluvial fans and deposition of sediments within the playa, including evaporites. But there's another vital agent, wind. This dust storm in the Sahara shows how fine sediment can be blown hundreds of metres into the air and transported on the wind for many kilometres. But in aeolian transport, the bulk of the sand-sized sediment is carried in a thick carpet just above the surface of the sediment. While the finer sediments may be carried in suspension by the wind, most of the sand-sized grains move in a series of small leaps and bounds known as saltation. Some larger grains are moved by continual bombardment with smaller grains in a process called creep. But none of these processes is capable of moving large grains. So wind-blown sands consist of a much narrower range of grain sizes than water-lane sediments. As in water, wind-blown sands form ripples, which migrate downwind as sand is stripped off the windward slope and redeposited on the lee slope. To identify sandstones formed in ancient deserts, we need to study modern dunes to determine the features of wind-blown sands that are likely to be preserved in the sedimentary record. Dunes migrate slowly, and their shape reflects long-term wind directions. If one wind direction dominates throughout the year, long linear dunes develop, seaf dunes. In contrast, when winds are very variable throughout the year, huge pinnacle-like dunes occur. This vertical aerial photo taken in the Sahara shows why these bed forms are known as star dunes. These curved-crested dunes are slowly migrating along Death Valley in the direction of the prevailing wind. Such smaller-scale bed forms usually occur on top of the larger seaf and star dune forms. Barkhans are isolated crescent-shaped dunes, the crests of which curve round through 180 degrees. A dune migrates by wind stripping sand off its windward side, and as the sand-laden air flows over the crest, so sand falls out of suspension to form grainfall deposits on the lee slope. This movement of sand and wind over the dune produces a gentle windward slope and a lee slope consisting of a steep upper section and a gentler basal apron. Several processes operate as the dune migrates, giving the dune its internal structure. Grainfall deposits accumulate on the upper part of the lee slope, and sooner or later they become unstable. Each avalanche produces a tongue-shaped deposit of sand, tapering at the edges, but with little internal structure. Avalanches only affect the upper section of the lee slope, the slip face. They don't extend right to the bottom of the lee slope, and the basal apron remains undisturbed. A series of avalanches down the slip face produces cross-bedding. This is picked out by small variations in grain size and colour at the interface between successive avalanche deposits. However, structures will only be preserved when there is net accumulation of sand, so that dunes are buried by the migration of subsequent dunes. But it is very rare for a dune to be buried complete. Usually, erosion on the windward slope removes the upper part of the structure, leaving a sequence of cross-bedded strata, each representing maybe as little as a quarter of the original crest height of the dune. There are also flatter inter-dune areas, similar to the player deposits, consisting mostly of silts. After heavy rainfall, they dry, forming polygonal cracks, which are then infilled with blown sand. So interdune deposits are a third feature which may be preserved in the rock record. Despite the hostile environment, the dunes are far from lifeless. So in amongst the dunes, animal tracks, burrows, and even plant roots may be preserved. In places, the wind has blown most of the sand away to leave a rock-strewn pavement. Many of the large clasts have been sandblasted by the wind. They were turned over occasionally by flood events, so that different sides of them become planed off by wind erosion. The end result is a pebble with several flat sides like this one. In Death Valley, we've seen a wide variety of modern desert processes, but can we recognise the evidence for these in ancient deposits? To find out, let's return to the Vale of Eden. to a good exposure of red sandstones. Using a computer, we've removed some of the masking effects of lichens growing on the face.
Doing that, what structure can you see in this face? Well, quite obviously, there are laminae or beds dipping fairly steeply, well, 20-25 degrees down to the right. And as they come in this direction, as they come down, the dip slackens off. And if we look up the face a little, we find that some of these laminae are eroded off, they're truncated. And then above that truncation surface is yet another set of cross strata showing pretty well the same geometry. Now when we go round the corner at right angles to this face, the bedding looks virtually horizontal. So this is telling us that in the other face, the first face we looked at, we're seeing the maximum dip on the cross strata. So now we can get a pretty good idea of what the shape of these surfaces producing the cross strata were. They are in fact curved surfaces, and the curvature is slackening off towards the base of the structure. So it's obvious then that we had rather large bed forms. We've got at least 2 meters preserved in each case, and remember, maybe a half or even more of the structure has actually been truncated along that truncation surface.
Another face in the quarry shows some additional features of these bed forms.
Well, this face looks completely different to the other one. The laminae are dipping in both directions, down to the right and down to the left. Let's look what happens to them from the base of the quarry face upwards. They dip towards the left from the base, and as we go up 2-3 meters about, perhaps nearly 4, there's a truncation surface dipping gently down to the right that cuts that set off. But then follow the truncation surface up to the left. It's cut off by yet another truncation surface that sweeps right down across the face towards the left. So things are looking a bit different here. So clearly not all the cross stratification in this quarry is just simple sort of cylindrical dipping surfaces. There's something more going on here. And when a whole series of dip measurements are made on these strata, there's a huge variation through almost 180 degrees in variation in the dip direction. So what we need to do now is to try and explain all the features we've seen, the variety of cross stratification features and the variation in the dip direction, by thinking what kind of three-dimensional bed form could have produced these structures. Well, we've got to think of a bed form that could give us a 180-degree variation in dip direction. Well, clearly it must be a curved crested bed form. And I've drawn what it could have looked like on this plan view. So the current would have flowed from top to bottom across the board, and here is the bed form with its steep slip face dipping down current and its more gentle up current face. So now you can see that there would be a considerable variation in the dip on this slip face. And as the current flowed over it, sediment would be transported, even eroded from this surface and deposited on this one. And we can see that in the section. So current flowing in that direction, material possibly eroded from this surface and then deposited on the slip face. So the structure moves down current, and so this would go on. And as it did so, we would get the cross strata produced here. And the variation in the dip of that cross strata is explained by the curvature on the bed form. Well, what we've got to remember is that there's not just one of these bed forms migrating down current, there's a whole herd of them. So another one later might come and overlap this one. Here's the steep slip face, and there's the more gentle upcurrent face. Now think about the dips here. In the lower one, the dips here would be towards the bottom left of the board, but the upper bed form as it migrated in would have dips down to the bottom right of the board, almost opposing each other, and that's exactly what we saw down in one of the quarry faces. So what I've been careful not to say so far is whether these were wind currents or water currents. So now we need to look for evidence to see if we can decide which one, and that means looking at the sediment itself much more closely. So let's go and do that. Well, this piece is clearly a medium grain sandstone. The dominant mineral present is quartz. The grains are sub to well rounded, extremely well sorted, and in places I can see some frosting to the grains.
The red colour must be due to a red coating I can see on the grains. This must be hematite, and this is particularly clear when we look at the sandstone in thin section.
So, have we seen anything to distinguish whether these sediments were laid down by wind or by water? We can get well-sorted sediments in either wind or water, but the key thing is the frosting. That is a common feature of wind-blown sand grains. So I can be pretty confident here that we are dealing with a wind-blown sediment. And there are other features here on a slightly larger scale that are worth looking at. In this part of the face, it's obvious that there are some grain size variations. In several places there's medium grain sandstone, similar to that I've just been looking at with the hand lens, here, here, and in this part. But there's also some coarser intervals. Coarse sand here, and one here. And this one shows some grain size variation. It's coarsening up, and it's capped by some laminae of very fine grained sand. So what's the significance of these changes in grain size? Not only the alternation of coarse and medium sand, but the fact that some of the coarser units actually coarsen up and have sharp tops. Well, maybe it could be a variation in wind velocity, but more likely in the case of these little units is that they are the products of avalanches down the slip face of the bed form, something that's commonly seen in deserts. So now we've built up a series of observations, related them to desert processes, and leaving us in no doubt that these sediments were deposited by a series of migrating bark-end dunes migrating along the Vale of Eden. Well, usually when I come to this quarry, the sun's shining, but whether rain or sun, there's usually rock climbers doing their first climb here. Well, this is completely different to the previous exposure. What do you notice about the clast sizes here? Well, there's very large clasts. This is a red and limestone clast, at least 30 centimetres across, but immediately above it there's much finer grain material. Granule size, even down to coarse, maybe even medium grain sandstone. And the shape of the clasts, well, some of them are rounded, like the top of this one here, but some of these are quite angular. And the composition of these clasts are pretty well all Carboniferous limestone, which is fairly soft. So if we've still got angular surfaces on these clasts, then they cannot have been transported very far. So that's another clue to depositional process and environmental setting. But they're not all limestones. Very occasionally we actually see some chert pebbles. There's one there, very angular, not surprisingly, as it's so hard, and cherts are quite common in parts of the Carboniferous limestone. And very occasionally we get red sandstones, such as this one, and there's another one over here. Probably a Permian sandstone that was deposited almost simultaneously with all these sediments and then ripped up again from somewhere else and brought here. So once you get your eye into these faces, it's possible to see that there's quite a bit of organisation of the different sediment types. Here's the base of a breccia. The grain size doesn't change much, but then it begins to fine, and there's a transition up into this low-angle cross-stratified sand, coarse sand. And then there's another breccia comes in, and that definitely gets finer upwards, passes up into granule-sized sediments, then into some more low-angle cross-stratification with coarse sand and granules, and then yet another breccia on top of that. So to sum up then, we've clearly got a variable energy here, because there is variation in grain size from very big clasts like this one, 30 centimetres across, to coarse sand just above. And there are discrete packages of the sediment. So that suggests that maybe there were a series of high-energy events separated by long periods of non-deposition represented by these bedding planes. Where do we find such high-energy processes? Really, the only two options are beach or river. If it was a beach, what would the shape of the clast likely to be? Rounded and well sorted. Clearly not the case here. So really, we're left only with the river option. And the composition of the clasts, being largely limestones, suggests that they were derived fairly locally. And this division into packages, or almost events, is very similar to what we see on modern alluvial fans in desert environments. Supporting evidence for that too is the fact that some of these limestones, like this clast, are reddened. And these may well have been derived from near the top of the weathering zone. So desert weathering would have led to this red coloration. So this backs up this idea of a desert setting and an alluvial fan, just like the ones we saw in Death Valley. Well, we've seen evidence in this part of the Vale of Eden for the presence of alluvial fans that deposited these coarse, poorly sorted angular sediments behind me, and also for dune sands, the cross-bedded sands that we looked at earlier. Now, what's the spatial relationship between these two? Well, using paleocurrent data and mapping the facies out, we think that the alluvial fans spread from west to east off the flanks really of the Lake District and filled the Vale of Eden, and the dune sands are thought to have existed down the axis of the Vale of Eden. So that's how the two would have interfingered with each other. You may find it surprising that probably not much alluvial fan material was being shed off the huge Pennine fault scarp, and this was because the newly formed fault topography would have meant that most of the river drainage was away from the scarp, towards the east, into the present-day Pennines.
So there is clear evidence that the Vale of Eden was a desert area during the Permian, and so was the rest of Britain and the rest of northwest Europe. In fact, the paleogeography of the area during the early Permian was very similar to that of the Arabian Peninsula today. Back then, it was possible to walk across the North Sea, the southern part of which was a large player lake, shown in blue. The flat player was flanked by desert dune sands, shown in yellow, and river deposits, mostly deposited in alluvial fans, shown in orange. The rivers, which flowed only after infrequent storms, drained highland areas surrounding the southern Permian Basin. These areas are shown in brown. The fact that northwest Europe was once a desert in Permian times is of great economic significance. This is because the desert sands and some of the alluvial fan sediments are good reservoir rocks in which gas has accumulated. The gas was driven off underlying Carboniferous coals as they were deeply buried later in Mesozoic and Tertiary times. So continental drift has left us a wonderful legacy. Coal formed in equatorial swampy conditions as Britain lay near the equator. As it drifted northwards, porous desert sands accumulated in the early Permian. Finally, during the late Permian, the desert area was flooded several times by the sea. But as the region was still in a hot, dry climate zone, the sea periodically evaporated to produce thick deposits of evaporite minerals, including halite. These evaporites are the icing on our economic cake that ensured that natural gas has remained trapped in the porous desert sand.